this great stuff that gives you geometry and then relationships and all that. And we always have a family day where we put out a lot of good stuff, and the children go crazy about it. When they're really excited, they say, that's mathematics.
Yeah.
So hopefully the next generation has a better attitude towards mathematics.
Yeah.
Jeff, I think it's time.
1 year.
All right. Good afternoon, everybody. Welcome to the first of our EECS Department Colloquium every Wednesday, or almost every Wednesday at this time. And it's a great pleasure to kick off this semester with our own Professor Yablonovitch. Eli is an amazing guy. He has made contributions to science and technology across a wide range of disciplines and areas that have all made amazing impact. Eli is the, let's say, father of the technology that's used in every optical communications laser today, strained layers. He is the inventor of photonic crystals, which are seeing widespread use now in all kinds of imaging and optical communications and all kinds of applications like that. He has made incredible contributions in solar photovoltaics. At one point held the record for the highest efficiency solar cell, has still, and is responsible for teaching the whole field a number of really basic yet surprising to some facts about how to make efficient solar cells, and a number of other things. And so he, every once in a while, he just goes off in some random direction that seems random to most of us and makes a big impact. And I think that's what we're going to hear about today, is his latest foray into a completely different field, namely that of the climate crisis and carbon in the atmosphere. And so I can't wait to hear about Eli's great idea about how to solve literally the entire problem of the climate crisis in an economical way. And that's the title of his talk, so I introduce Eli Yablonovitch.
Jeff, thank you very much. So I should mention, before I get started, my co-author, Harry Deckman, who is someone I used to work with 40 years ago. And we've kept up our intellectual...
Is the sound muted on?
Oh, I'm still muted. Okay, you can hear me now? It's okay. All right, so let me say, I think we've heard plenty about the climate crisis, and we're trying to go carbon neutral, but there are some things that are very difficult to deal with and to correct. For example, there are functions for which it's very difficult to replace hydrocarbon fuel, unfortunately. So one example is international aviation, which depends very much upon the megajoules per kilogram of the fuel, and it's very difficult to do better than jet fuel. Another problem that we haven't solved is summer-winter energy storage, which is very challenging. Most energy storage, they talk about batteries, but now when you talk about summer and winter, which is probably the most important type of energy storage, it's something that has to be rock bottom cheap, and you'll use it only once a year, so it's a problem. And then another problem is there will always be countries that do not cooperate, okay? And so what it says is that carbon in the atmosphere will grow unless we find a way to extract it. And then there's a fourth thing to worry about, and that is that there are some very credible models that suggest that positive feedback of CO2 from permafrost can lead to a thermal runaway, which is to say that being carbon neutral will not help that. We actually have to go back and pull that carbon dioxide, that historical carbon dioxide, out of the air to prevent that. So it means we need carbon negative technology. Now, this was controversial up until about 9 years ago. And then people noticed that this was an issue. So the various national academies all over the world came out with reports and basically saying, okay, here are some ways to do carbon dioxide removal. And just to show that the Europeans are not far behind, so they wrote a report about 5 years ago on negative emissions. So it's now reached a point that people are realizing this has to be done. And carbon negativity has become a thing. And here's an article in Physics Today, but there are many examples. I would say the conventional wisdom now is that we do need to have carbon negative technology. Now, one of the ways of doing that is to actually, well, this is not a great way to do it. You force the atmosphere essentially through a pipe, and in the pipe you have amines which capture CO2, and you can imagine this is not going to be cheap. Essentially, you solve the problem by passing the entire atmosphere through a pipe, so that's not going to work. In fact, the most optimistic estimates say $600 a ton, but the things that are being funded now are more like $1,000 a ton, which is very expensive. And I will calibrate, because I know you don't go often to the supermarket to buy a ton of CO2, so I have to calibrate it in terms of things that you know about. I think I'll do that in a couple of slides. So if you look at the European report, they proposed a number of options, controlling forestry, reforestation, etc., land management to increase carbon in soils, bioenergy, so you burn biomass and then you capture the CO2 and then pump the CO2 underground. And then there are certain rocks that actually absorb CO2. There are not very many, but the process has very slow kinetics. So it's not very practical. And then I already mentioned the direct air capture, which is very expensive. And another idea that's out there is ocean fertilization, and then they hope that they will promote the algae growth, and the algae will fall to the bottom of the sea. But it's people say very little of it falls. So of all these, I think they have ignored the most obvious candidate, which is to grow biomass, and instead of making biofuel out of it, just to bury it. So how do you do the safe burial of agricultural biomass? And we call that agro-sequestration. That's what I'm going to talk about. Now, who was the first one who came up with this? And so this is why it's this talk maybe does belong here, in at least among the electrical engineers, is Freeman Dyson, one of the most famous physicists, and surprisingly, he was truly, maybe Jeff gave me too much credit for being a jack of all trades, but he was truly a Renaissance man, and he covered everything, and he already proposed this exact idea in 1976. So this is kind of amazing, and what he said is we grow some kind of tree, and we bury the tree, and he says, and that solves the problem. Okay, so well, you didn't hear much about it. Perhaps we should have heard more. Here's another example of carbon removal that has become very big now, is that the X Prize committee is in the middle of a competition to find the best way to remove carbon. And the $100 million prize, and the first prize is going to be $50 million. But you have to remove 1,000 tons. Now, let me mention one fundamental scientific thing that makes it difficult to pull carbon out of the air. The concentration is very low. And when the concentration is very low, you see the carbon dioxide can be here, it can be there. You're not sure where it is because there's so little of it. And so there's entropy associated with the dilute concentration of carbon, and you do K log of the diluteness, and you end up with a certain amount of entropy, and that converts to free energy, which is not enormous, but still very difficult to deal with. And so to pull carbon out of the air, you have to supply some form of energy. Of course, if you pull it out in the form of biomass, the plants will through their photosynthesis, will provide the free energy. So this is one of the difficulties of pulling carbon out of the air. Now, so which plants? So I'm relying very heavily on the biofuel people who've already studied this in great detail starting about 15 years ago. So here at Berkeley, biofuel became kind of a big thing. And in every region, there's an ideal crop. In the Midwest of the United States, it's something called miscanthus, but they have other crops, for example, that are more adapted to the Caribbean. And so this has been worked out, and the agriculture stuff has been worked out. The cost of the agriculture. By the way, every country publishes agricultural statistics, and because it's so important. So what happens then is that we have these different crops, and now these crops are not something you can eat. It's cellulose. It's not really a very good food. And so the insects don't like it, and so it's easier to grow these types of crops than it is to grow something like corn. And of course, I gave this talk in Europe, so I had to use maize so they wouldn't get confused about corn. And if you grow these non-food crops, you get greater productivity, about 3 times more than a major food crop like corn. And then you pull out 44% by weight carbon, and in 1 acre you can extract 5 tons in every growing season, and then it would take a certain large number of acres to extract the annual fossil fuel from the atmosphere. So that's sort of the plan. So let me mention this gentleman. So there was a time, and Jeff was kind enough to mention that I had done some work on solar energy. And in fact, my mentor at that time is a gentleman who should be famous. He's probably not very famous, but he should be. He graduated from Cornell in 1938 and went to work at RCA and invented the Vidicon camera, which is the camera that all of television used until the charge-coupled device. So from 1940 to 1980, television, if you watch television, you were watching through the eyes of a Vidicon camera. So he was a very distinguished scientist in that regard. But he, in his later life, when I got to know him, he became very interested in solar energy. And I was working on solar energy. He was kind of like a consultant at the company I was working at. And he told me one day, Eli, on your way to work, you passed some gas stations, and the price, so it was 1979, and the price of gasoline was in one of its energy crises, and the price of gasoline had gone very high. And he said, why don't you figure out the cost of gasoline, not per gallon, but you figure it out per joule, per 100 megajoules, actually, decent unit, 100 megajoules. And then go look up in the Wall Street Journal, look up on the Chicago Board of Trade, what is the price of corn per bushel? And of course, the challenge in that calculation is to convert bushels into metric units. Okay, so I did do that. And I was very shocked that, in fact, the price of gasoline at that time was pretty much the same as the price of corn. And you think that corn as a food is valuable and so on. So I was rather surprised that agriculture could be so efficient. Well, it turned out I looked it up, and he had already figured the whole thing out. He was testing me, but he had just published it about a year earlier before he asked me that little riddle. So the purpose of this slide is to have some respect for agriculture that is actually very efficient, and you could grow the biomass, which is not food, which is cellulose. That is a very efficient form of agriculture, and you throw it into the ground in a modern landfill. So what's a modern landfill? When you had breakfast this morning, you undoubtedly generated some garbage. That garbage ended up in a landfill, and the modern landfills, and I don't doubt that California has the most modern landfills, they are sealed off with 4 millimeters of polyethylene. And that's important to us. Of course, the reason they're sealing it in polyethylene, they don't want the garbage to contaminate the groundwater. And what I'll show you is that we actually, we will grow some biomass. We have to keep it dry. And now, so we have to do in reverse. We don't want the groundwater to come in and mess up the dry biomass, because to preserve it for a long time, you need to keep the biomass dry. So I wrote a paper on this with my co-author, Harry Deckman, and was published a few months ago in the Proceedings of the National Academy of Sciences. Now, if you go back to what we heard from Freeman Dyson, he was just going to throw logs in the ground. That doesn't really work, because if you just throw things in the ground, it decomposes and you get back your carbon dioxide, and worse, you get back some methane with it. So that's not very good. You think, well, if I have it anaerobic, maybe that'll help. Actually, no, there's plenty of microbes, fungi, and anaerobic things that will decompose even when there's no oxygen present. And this is a problem. You end up producing CO2, and you end up also producing methane, which is sort of worse than what you started with. And so we have to correct Freeman Dyson a little bit on that. And so the simple burial is still very attractive, and I thought of it a long time ago. I've been thinking about this for 40 years, and but I ran into a roadblock. Simple burial doesn't work. If you make it anaerobic, it still doesn't work. And so what do you do? And so it was only a couple of years ago that my co-author came to realize that there is a way of making the burial work, and that is to keep the biomass dry. And I'll show you some slides on that. But here's what happens in decomposition. You get back your CO2 and you get methane. Now, what people like to do is to bury wood. And sometimes, and I don't know if anyone has been digging in their backyard, maybe you're doing some horticulture and you're trying to plant something, and you dig up a board that the contractor left there decades ago when the house was built. And you dig up the board and you hold it, and it looks like a board. It has all the appearance of a board, but it's very lightweight. It weighs almost nothing. Well, it weighs a lot less than expected. And the reason is that wood is composed of, has two major components. You have cellulose and you have lignin. Now, lignin is the part of the wood that makes the grain of the wood, and it's present, it's a fairly high concentration, 30% lignin. So what happens is that all of the cellulose decomposes very quickly. But the lignin turns out to be a very, very difficult material to deal with. For example, the biofuel people, they were always troubled by lignin. It's so stable, they could not convert it to biofuel. And so what happens is that that board that you picked up that had only like incomplete weight, it didn't weigh what a board should have weighed, is the cellulose was gone, but the shape of the board was still there. And so you see this in museums. They will dig up some old thing, and it still looks like it's there. So maybe some old ship. I remember once in Stockholm they dug up an old ship from the harbor, and the lignin is still there, but you've given up 70% of your biomass. So yes, you've got some benefit. You've managed to store the lignin, but you're sort of inefficient because only 30% of the wood ends up being sequestered. So this is something that it is maybe a little controversial among my colleagues, because I can point to 7 startups. They're just going to bury wood. And it's kind of tough to explain. I'm sorry that doesn't work, so it's a little tough to explain to them. Now, so now we get a little scientific. And so I mentioned that the solution to the problem of decomposition is dryness. So now we have to sort of define what is dryness. I think everybody here knows what relative humidity is. So I have here a picture of a steak. And if I ask you, well, what is the dampness. How, what's the humidity of the steak? And so, well, it's air has a relative humidity. Steaks do not have relative humidity. So how do you know the steak is dry? So the chemists have introduced a concept called water activity. So water activity is the equivalent to relative humidity in air. So if you have 60% relative humidity in air, then if you let the steak dry, it will end up with 60% water activity. And all biomass has water activity. And if the biomass is very dry, it might have a low water activity. And why do I bring up the water activity? Is that metabolism, the decomposition requires metabolism, and the metabolism requires water to move the chemicals around inside the cell. And so surprisingly, maybe not so surprisingly, metabolic activity stops if the water activity is less than 60%. So this is kind of an interesting fact. So this is sort of the scientific part. So you ask, well, what about, how dry does it have to be? So here's an interesting factoid. When farmers are selling corn on the Chicago Board of Trade, they have to dry the corn because the Chicago Board of Trade will not accept corn that has more than 14% moisture in it. So 14% moisture by weight would come out about here, and that would come out to be maybe around 60% water activity. So in order to get down to 60% water activity, you have to dry the corn to 14%. That's actually not that difficult to do because they've been selling corn in the Midwest for 150 years, and the farmers used to dry the crop. They just leave it out, and it was dry enough, and they put protection against rain and so forth, and it would be dry enough. Of course, today the farmers don't do that. What the farmers do these days is they use propane or something of that sort to dry the crop. So this is this drying of food is an ancient principle for food preservation. So this is from the Indians in the Northwest drying salmon. These are little hunks of salmon. They would dry it. And you say, well, how dry does it have to be so that it doesn't decompose? And yeah, as soon as you make it dry, it gets hard. So already many bacteria give up at 95%. Yeasts, mildews, and so forth. And you go down, and fewer living things can survive if it's very, very dry. And who has studied this? NASA has studied this because you want to discover life on other planets. You need to know, well, how much moisture does life need? And so it needs 60% water activity. And the other government agency that has studied this in great detail is the Food and Drug Administration. Because let's say you have some type of food, you wrap it, and it's dry, and you wrap it in cellophane. Are you allowed to put it on the shelf? How do you know it's not going to spoil on the shelf? So the Food and Drug Administration checks the water activity, says, oh, it's dry enough, you can leave it on the shelf in the supermarket. And so this has been studied both by NASA and the Food and Drug Administration. So 60% of water activity is the boundary. Now, there are a couple of ways of doing it. You can dry it very thoroughly, and that works. Another thing you can do is add a little bit of salt. So to get down to 60%, it turns out sodium chloride doesn't quite do it, but magnesium chloride does it, and there are other salts that will get you below the 60% water activity. Of course, this has been known since biblical times that salt acts as a food preservative and was extremely valuable in the Roman Empire for that reason. So this is a little bit of scientific part, which is the fraction of water in the food on this axis, fraction of water, and the water activity. And so that's kind of interesting. So why does salt help? Because salt displaces water, gets into solution, displaces water molecules. If you have fewer water molecules, you have lower vapor pressure, and that gives you a lower water activity. And if you have a divalent salt, it's even more effective because then the salt molecules cluster around the divalent salt, and it works even better. So these are some options, but you can just do some more aggressive drying. But calcium chloride is a famous salt that is used for these purposes. And if you have lived on the East Coast during the winter, the salt that they throw on the highway is not sodium chloride, it's calcium chloride. It's a relatively benign salt, and so they can just throw it on the ground and not worry about it. But it has this great property is that you can easily drop below 0.6 water activity with calcium chloride. Or you can just dry it more thoroughly. So if you build one of these landfills, how big does it have to be? It would occupy about 1/10,000th the area of the land that is used for the agriculture itself. And then when you're done with it, you just throw dirt back on top of it, and it's good for agriculture again. Now, what is the key thing is that you do need to seal it off. But this is an existing technology for landfills. It is rather thick. It's 4 millimeters of polyethylene. Polyethylene doesn't like water, so the diffusion is very slow. The diffusion of 4 millimeters of polyethylene to water is equivalent to 1.7 microns of water every year. And so for that reason, it lasts a very long time, thousands of years. Okay, so that gives you some idea of what the solution is that we're proposing. Now, what is the size of the problem? I have a whole bunch of calculations here, but it comes out to be that you've got to pull, every year you have to pull 20 gigatons of CO2 out of the atmosphere. So it's a lot. But it has already been studied thoroughly by the biofuel people. And these are some of the papers that they wrote on this. And here's a Department of Energy report on how to get to the gigaton level. And so from those, you can put them together and figure out how much land, how much agriculture are you going to need. And so you can look up the availability of agricultural land. And of course, there's the poles that are covered in ice, and there's other land that is completely hopeless. But there's also normal agriculture, there's forest, there's shrubs, and so on and so forth. So let's look at the normal agriculture. Most of it is used for pasture. Only 11% of the Earth's surface is used for row crops, which is kind of interesting. And what is the land needed to pull the carbon dioxide out of the air? So the land is represented by this blue rectangle. So it's a fraction of the agricultural lands. And in this analysis from the Department of Energy, they split it between pasture, forest, shrubland, and other forms of land that are underutilized. Well, I'm going to show you a slide very shortly that agricultural land, surprisingly, is underutilized. And this is sort of an indication of that. You've all heard about the green revolution, the agricultural revolution. And certainly in terms of labor, human labor, we've become way efficient by over 100 times since Malthus predicted very pessimistically that the Industrial Revolution wouldn't help because people would still have too many children. There would never be enough food for them. But he was wrong. In fact, you can see here on this graph that the productivity of land in the least developed countries has improved about 2x over a 50-year period. In fact, I went and we searched and we found some data that started in England in the 1700s of the productivity of land for growing wheat. And this is rather interesting data because then you have, they didn't have hectares back then. They had very strange units of land in that era of British history. But let's start the graph at 1800. Malthus makes his very pessimistic prediction, but between 1800 and 1900, the productivity of land doubled. This is the reason why his prediction of overpopulation didn't work out. And then something happened at the beginning of the 1900s, the Haber process. And the Haber process, a method of producing artificial fertilizer, and so it fell onto a faster curve. So every 50 years, let's say in the first half of the 20th century, doubled, and then second half doubled again. So since the 1800s, since Malthus made his negative prediction, you had an exponential increase in the productivity of land. And this is in real units, so it's tons of wheat per hectare of land. And so likewise, the United States followed the same track. And so the current situation for the productivity of land is that there is a Moore's Law for agriculture. The Moore's Law is way slower than the Moore's Law that we are accustomed to, but it has been doubling every 50 years. Now I say, well, it's saturating. We've gone as far as we can with fertilizer, but wait a minute, we have CRISPR now, and many other technologies that are going to improve the productivity of the land.
Why is the productivity in the U.S. so much less than Britain?
That is a very good question, and the reason is the land is so much cheaper in the U.S. than in Britain that rather than putting more inputs into the land to get more productivity out,
Just use more land.
They just use more land. And in the European Union, of course, they're trying to be self-sufficient in food, and so they subsidize all the farmers, and they put a lot of input, a lot of effort in, and in Britain, they have higher productivity, and throughout the European Union, that's the case. But I expect that might continue. Now, here's a graph showing you a similar fact, is that to grow a fixed amount of food, the amount of land needed has gone down. And it's gone down by roughly 1/8. It's 68% less land after 50 years, starting, the baseline was 1961. 68% less land to produce the same amount of food. So it's giving you some idea of the agriculture is doing very well. And actually, I can, as a solar cell person myself, I can calibrate how far we can go with agriculture. So if you grow corn, the efficiency is 2%. But it's food and nobody complains, and it's gotten better over the years and so on and so forth. Now, if you get the record-breaking solar panel is 29.1%. So what has nature done wrong? After 100 million years of evolution, the agriculture is nowhere near as good as the solar panels. And by the way, the process is very similar. In a solar panel or in a solar cell, you have separation of quasi-Fermi levels, and sometimes we call it a chemical potential. Of course, this was invented by chemists, not by physicists. And if you have an energy-rich molecule present, let's say in a crop or in your body, we can talk about the chemical potential just the same as we would in a solar cell. So the physics of photosynthesis is very similar to the physics inside solar cells. So what that suggests is that great improvements are possible. So let's say we do a factor 2, then, well, that only gets us to 4% efficiency, a long way to go. Another factor 2 gets us 8% efficiency, and so on. And of course, if we had started with that's starting with corn. Let's start with something more efficient, like the biofuel plants, and it suggests that 3 more factors of 2 are possible, and it's going to take CRISPR and other forms of genetic manipulation to give us strains of both food and of biofuel that are much more efficient. And indeed, the efficiency arises from experience. So humanity has had about 10,000 years of experience with agriculture and have made it more and more efficient. And also we can figure out what it costs, what agriculture costs. And if you're not sure, you can look up on the Chicago Board of Trade. You can look up the productivity of the land and look up the cost on the Chicago Board of Trade. It costs about $500 an acre to conduct agriculture. And so you can get an idea of what the biofuel product will cost, or you can do it the hard way and just add up all the inputs and you get the same answer. And so here's what it costs. So if you convert to the biofuel or the biomass to tons of CO2, the price is about 30. I'm not going to look at the fine differences between the pine trees and the switchgrass and so forth. It costs about $30 a ton to grow the biomass. And then you say, well, what about the landfill? Well, we know how to build landfills, and we're continually building them because we're always creating garbage. And so the landfill also costs about $30 a ton. So if you combine them, it ends up as $60 a ton. And that's the projected cost. So $60 a ton. Now I'm going to convert it to units that we're more accustomed to. So this is, somebody sent me an email, a professor sent me an email that said, oh, this is such a great idea, I have to teach it to my students, I'll give them a problem. And I said, oh my God, some of these are hard concepts. But this is one that's suitable for college students. If you're paying $60 a ton of CO2, what is that going to cost for something that you're familiar with paying for, which is a gallon of gasoline? So that's a conversion, essentially conversion of units, and works out to be 53 cents a gallon. So this process would add 53 cents a gallon to gasoline. And we're trying to get rid of 20 gigatons, and the world gross national product is 100 teradollars. Yeah, these are teradollars, thank you. So, okay, we're going to pull every year we're going to pull all the carbon dioxide out of the air. At this price, at $60 a ton, what is it going to cost? It's, well, it's 1.2 teradollars. I mean, it's a lot, but it's like 1.2% of the world economy. So it's doable. So we sent the paper off to be published, and the referee came back and said, okay, reasonable paper, but you have to find some natural experiment that proves that this is really going to work, that you can point to. And so we actually figured it out before we should have included it in the paper. And so I'm going to show you, it's not exactly a natural experiment, but it's an experiment that was created or started 2,000 years ago. So I'm going to tell you that story. It's a very interesting story. So in Israel, there is a very famous mesa that is famous for the last, it was the massacre, not the massacre, but actually the suicide of the last holdouts against the Romans. And so they laid siege to this mesa, and they were up here. But it's kind of interesting, that's why tourists go there, but there's something else there that's of great importance to us. I should mention something about this mesa, is it's adjacent to the Dead Sea. The Dead Sea used to come right up to the shores, right up to the edge of the mesa. And the top of the mesa is roughly at sea level, and the bottom of the mesa is about 1,200 feet below sea level. So it's very steep walls, but what happens is that they had a king in Israel, King Herod, and like most kings, he was afraid of being overthrown. And so he built a palace. It's not exactly a palace, it's more of a fortress. He built it up here, and he left it there, and it had been abandoned for thousands of years. And then, so this is King Herod. This is the story. King Herod builds his fortress up there, never uses it. It gets sort of abandoned. And then there's this guy, an Israeli, he was actually had an appointment in the armed forces, but he was really an archaeologist. So in 1965, he excavates the palace, and he found, or fortress, whatever you want to call it, And then he finds some seeds of the date palm tree, and these seeds are big like pecans. They're about that big. And he's an archaeologist. He doesn't know what to do with them. He leaves them in a drawer, and then he passes away. And a doctor, an actual medical doctor at the hospital in Jerusalem hears about this, and she sweet talks whoever's in charge of this archaeologist's records to give her some of these seeds. And then she sends the seeds out to be carbon dated. They are indeed 2,000 years old. And then she gives the seeds to this woman who is a horticulturalist and who germinates the seeds. And the seeds germinate. These are the seeds. They germinate. They give you a little plant. Eventually give you a bigger plant and a bigger plant, and then eventually becomes this plant. And this this picture is actually figure 5 of our paper. So we had to revise our paper to include this, to show that there is an example that if you keep things very dry, that the biomass will be preserved for thousands of years. So that satisfied the referee. We managed to get this published. This tree is 18 years old, and it's surrounded by a fence because it's of historical importance. But there are between half a dozen to a dozen of these trees that have been germinated and are historical curiosities. So what it shows is the DNA was preserved for thousands of years, and okay. I need to tell you one more thing about biomass that I forgot to mention. Let me use a little white space here. If you grow biomass and you convert it to biofuel, so what is the biomass? The chemical formula for the biomass is roughly this. So the biomass is already partially oxidized. So if you want to convert it into fuel, you really need 2 of these molecules. So that you can get rid of one of them as CO2 and then maybe sequester the CO2, but then you'd have some fuel left over. So the sequestration is twice as efficient as making a biofuel, because you've got to grow 2 acres to get 1 acre of biofuel. And so this is just a little factoid to keep in mind. Okay, so what are the prerequisites for solving the climate crisis? Well, you need scalability, as to say, is it big enough to deal with the problem? And agriculture is one of mankind's largest industries. So what about the cost? Well, the cost, I don't know, this doesn't sound so bad to me. 53 cents a gallon, I'm willing to pay that. And stability, and so we have proven sequestration over 2,000 years. And there are a lot of schemes out there that are interesting, exotic, and might work, but they are curiosities that you say, okay, if this is going to be a huge investment, it's going to affect the future of mankind, maybe you can come back in 2,000 years after you've proven it out. And this is something that essentially has been proven out. So the predictability. And so we don't need to do further experiments because the experiment has been done, and we can validate it. And the other thing is, we know there is a crisis and we keep postponing action. This is something, agriculture is something you can implement with the next growing season. And so we can start pulling carbon dioxide out of the air starting in April coming up. So what are the next steps? Certain scientific things we still need to study. For example, how low does the water activity really have to be? And for example, if instead of 0.6 we can get by with 0.75, which is kind of nice because then you can use ordinary salt for that. And then how do we deal with the transition from dry biomass to bury it dry? There's always a danger. What if there's a rainstorm, etc.? And so there's questions of how to sequence the construction, etc., of the bio landfill. And what is the ultimate limit? It looks like it's 0.61, but really need to firm this up with mass spectroscopic measurements of tiny amounts of decomposition. I think it matters for the future if it's 0.6 or 0.62 or down in that range. I think that's relevant. But this doesn't mean to suggest that we should stop conservation, abandon all alternative energy. We need to do all these things. We still need to do them, and we need an all of the above approach. So where are we today? Well, amazingly, 40% of U.S. corn is used for ethanol, and the process is far from carbon neutral. So it's not very good. So the actionable recommendations is the government, instead of subsidizing the farmers to grow excess corn, how about them growing miscanthus, and to build up some research test beds that would get this going. Of course, this would be very good because the farmers would be happy because you're creating a new cash crop for the farmers. So it's very politically acceptable to the farmers. So I would say at this point, the agro-sequestration appears to be the lowest cost, scalable, carbon negative technology. And in fact, in an emergency, it could remove historical carbon emissions. And that's part of being carbon negative, is you can actually go back decades and pull that old carbon dioxide out of the air. But we have to be careful of the moral hazard to say, okay, we've got it all figured out. I would say we need to continue research in new forms of energy and new ways of dealing with this problem. In fact, right now, we're, as you all know, we're living in uncharted territory, a very high carbon concentration that we haven't seen before. And carbon neutral is not good enough. We need to be carbon negative. And that agro-sequestration can actually do this at an acceptable cost. So that's my conclusion. Let me invite questions. Thank you very much for listening.
Okay. Questions?
Before you get started on the questions, let me put a little advertising slide. We are trying to commercialize this. I think it's part of turning it into a reality. So we're recruiting at all levels, from member of technical staff all the way to COs. So please email me CVs. Okay.
All right. You can't beat that. Okay.
Yeah, great, Eli. So actually, I didn't know that the process of, that it was so low, the efficiency was so low compared to photovoltaic. So that is a surprise to me.
Yes,
so,
agriculture is amazingly inefficient, and we could spend a whole talk on why.
Yeah,
why
photosynthesis. So
nature took that route.
I wanted to ask the why. So, so what is photosynthesis optimizing? So you suggested that CRISPR may be used to improve it, but will that cause other issues?
Okay, so I'm glad I stimulated it. It's a very interesting scientific question. We can only speculate why it is that agriculture is so inefficient compared to solar panels. And so I've thought about this a long time. I know I learned this 40 years ago from Al Rose, my mentor. And I would say that one way to think about it is that the vegetation does not necessarily optimize for efficiency. It optimizes for survival. In fact, all living things optimize for survival. And if the Earth was very peaceful, maybe it could just advertise or optimize for efficiency. But in fact, every plant that we see around us survived the asteroid collision of 70 million years ago. And so what happened? Light became very dim. It became very difficult to survive. And so the plants adapted to very harsh conditions, and they survived the asteroid collision. But they adapted to these harsh conditions by adapting to relatively weak sunlight. This is just a theory of why this happens. And indeed, the people who do the algae, the biggest problem with algae is they cannot withstand full sunlight. And so algae is actually is one of the big disappointments of the past 10 or 20 years, is that they never really resolved the issue of how do you use full sunlight. Algae doesn't accept full sunlight, and most crops do not, and or do it with great difficulty. They have a channel to just dissipate the excited molecules, dissipate the energy as heat. And but I think that's sort of kind of a hypothetical question. So it's just a speculative answer.
Anybody else? Any other questions? Yeah. That's a microphone for the video.
Why grow switchgrass or some specific kind of biomass when most of wheat, barley, corn is not edible, and you could use that as biomass?
Yes. In fact, this procedure that I described is sort of, doesn't really care. It's agnostic about the source of the biomass. There is quite a bit of agricultural sort of waste that's available. It's not that easy to do it economically, though, and the farmers like to leave that on the soil to help enrich the soil. So what we have in mind is crops that are dedicated to pulling carbon dioxide out of the air.
Yeah, but the cost of convincing the farmers to sell you the waste has to be competitive, at least, with the cost of growing it fresh.
You would think so, but the farmers are very hard to deal with. But we're sort of agnostic.
Sure.
Yes, some of that will happen. I mean, undoubtedly.
Any other questions? Okay, I have one. The historical experiment that you cited about the 2,000-year-old date palms it's kind of cute. It's kind of impressive. Sure, if you store seeds in Israel near the Dead Sea, where it's dry as a bone, then okay, it doesn't decompose. But you're proposing that that's not what you want to do. You want to bury the biomass underground where it's somewhat moist, and you're going to use salt to help reduce the amount of decomposition. So my question is, we have all this switchgrass or whatever it is. Somehow you have to mix it and get the salt, right, to diffuse all throughout the biomass in order for this to work. Isn't that right? And what about the cost for that?
Okay, so the salt is merely an example and an option. If you dry the crop sufficiently, then it has, just because the crop is dry, it can tolerate quite a bit of humidity before it goes up to 60% water activity. I think that's the way to analyze that, is that to some extent, maybe I should not have mentioned the salt, although it is kind of interesting that it works out. You made another point, though.
No, that was my point, was that in order to use the salt to suppress the decomposition, how do you actually, in practice, use that with these tons and tons of biomass?
You don't need the salt to prevent decomposition. What you need is a way to keep the crop dry. So the way it works out is you dry the crop, and you dry a little extra than normal, and then you put that into a landfill. The landfill is protected by 4 millimeters of polyethylene, which is not an unusual thing because that's what the landfills do today. And the 4 millimeters of polyethylene allow so little water diffusion that's good enough, according to the ability of the dry plant to safely take up tiny amounts of moisture and still be below the 60% threshold.
So you spent a lot of time kind of teaching us about the role of salt, but you're actually not proposing to use that.
Actually, one of the problems you bring up is the cost of the salt, because you can't use, sodium chloride is very cheap. Calcium chloride, which is the road salt, is the right kind of salt to use, but the they produce enough for de-icing the roads, but we're talking about maybe expanding that industry. So we don't want to get into too deep discussion about salt. It'll depend upon whether we can continue getting the calcium chloride at very low cost. Right now, the cost is very low, but we would have to expand the industry if we were to use it.
What I'm bringing up is that it's not just the cost of creating or forming the calcium chloride. I'm wondering what the cost is of effectively using it.
No,
You're going to somehow get it uniformly distributed
right,
all throughout
right.
the biomass.
And I'm saying that maybe we haven't completely thought that through.
Okay.
And but we don't have to think it through right now because we have the option of not using salt.
All right,
It's optional.
thanks. Any other questions before we close the,
So if you said that the algae are a disappointment, what about kelp? Is that something that you could throw in the sea?
Yeah, it's all a disappointment. Actually, kelp is a little bit better, but the problem is that you need to diffuse the carbon dioxide through the surface of the sea, and so this is not as good as growing plants on land, where you have the surface area of the leaves is much greater than the land area that it covers, and so the agricultural production in the ocean doesn't compete that well with the agricultural production on land.
all right, I think with that, we'll close, and thank Eli again for a really thought-provoking and exciting talk.